All right, everyone, welcome to our 15th lesson of the semester. So I have a few quick announcements before we get started here. So in case you didn't know, this Thursday is one of UF's, I think they called it recharge days. So it's our consolation prize for giving up spring break. So there won't be any discussion section Thursday if you have that. Also, my office hours are normally scheduled for Thursday, but those won't be there either. My office hours this week, I'm going to move it to 11 to 12 on Friday. So if you do have questions about what we've been doing recently, then feel free to stop by on Friday. But there won't be any office hours or any class-related stuff on Thursday. What about people with Tuesday discussions? Yes, you still do have discussions, but don't worry, you'll have your revenge later in the semester. There'll be a time where you don't have discussion, and then Thursday does. So it'll all balance out in the end. All right. Another thing is that I manually changed all of the grades from being out of 105 to out of 100, meaning I typed in all of it. So if you happen to see a mistake in what I typed, I combed over it, so I don't think there is. But if I copied your grade down incorrectly, let me know, and I will be happy to change that. All right. So anyways, let's go ahead and get started with the next section of the class. So we're going to leave integrals behind for the time being. We'll come back to them a little bit later. But now we're going to focus on something entirely different right here. So what we're going to start talking about is something called infinite series. Okay, and what is this? Well, an infinite series is where we add up infinitely many numbers together. And while that kind of sounds like an interesting philosophical question, why on earth would we care about something like that? Well, the good thing is that it allows us to make non-polynomial functions, oh my God, I can't spell, polynomial functions into infinitely long polynomials. So for example, cosine of x can be written as 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720. And the seemingly bizarre pattern continues on and on and on and on. Now, why on earth would we do this? I feel like most of you guys have a decent grasp on what cosine is. You probably know unit circle values, its relationship to other functions like sine. So why on earth would we want to cast it as this weird polynomial that seems to go on forever here? And the answer is you may not want to do that with cosine, but there may be functions that you encounter out there that are so hideously complicated that you don't want to deal with them directly. You would rather deal with a polynomial instead. Because the theme of this part of the course, here's the theme. The theme is that polynomials are nice. I guess the theme of the last part of the class would be integrals are hard, because we've learned all of these different integration techniques, and then there's still a lot of functions we can't integrate, and the applications can be kind of difficult. The theme of this part of the course is polynomials are nice. All right, here. Oh, is this a 120? No, it's a 720. 720. Well, I'll show you how we get that number later on, of course. But the theme of this part of the class is polynomials are nice. So rather than dealing with some hideously complicated function that may appear in some kind of application or something like that, like maybe you solved a complicated physics problem and you have this weird function as your answer, but you don't know what to do with it, you could instead turn it into a polynomial. And even things for something like cosine may actually be useful, because, for example, if you're programming cosine into a computer, your computer has no idea what this is. Like, it's not like someone sits there their whole life and types in a bunch of unit circle values in for the cosine, and then they kind of just spit them back out for your calculator. What they do instead is they input a bunch of terms of this polynomial. And while your calculator has no idea what cosine is, your calculator does know how to add, subtract, multiply, and divide. And that's all you need to do in order to compute what the value of a polynomial is. So if you ever want to know what cosine of like 0.268 is, it doesn't put it into here, it puts it into this polynomial here. So whenever you're implementing math onto a computer, which is an incredibly valuable skill, we're going to be using series for that by and large. So that's kind of the theme of the course here. We're trying to turn functions that aren't polynomials into polynomials because they're a lot easier to deal with. We know how to find their roots, but we know all the stuff about degrees and asymptotes. And then we also know how to do calculus with them easily. It's really easy to do the derivative of a polynomial, right? It's really easy to do the integral of a polynomial. So rather than doing something more complicated, we're instead going to try to do something easy. So that's the theme. And I'm going to continuously remind you of this theme throughout the next few lessons because it's going to take a little while for us to get here. Before we do this, before we have variables that are infinitely many variables that are added together, we first need to learn what infinitely many numbers added together means before we could replace it with a variable. And even before that, we need to address the infinite part of that. What does it mean to add infinitely many numbers together? So what we're going to do today is we're going to start off a little bit light. We're going to kind of start at the core of all this. This is going to be lesson 15. We're going to start with something called sequences. Okay, so what is a sequence? It's an infinitely long list of numbers. That's it. That's all a sequence is. It's just a really, infinitely long list of numbers. Is this like a binomial expansion? We're going to use some of the same notation as that, so that there is a kind of a relationship between those. Yeah, you'll see in a few lessons that might appear. Anyways, so a sequence is an infinitely long list of numbers. So let's write down some examples. So we have this is sequence 1, 2, 3, 4, 5, 6, 7. Can anyone guess what the next number is going to be? What do you think the next number is going to be? 8, that's right. And so it's just going to be all of the counting numbers starting from 1 and going up like that. All right, here's another example of a sequence. 3, 3, 3, 3, 3, 3, 3, 3, 3. And it's going to be threes in perpetuity like that. Here's another example of a sequence. So this goes to show you the sequences can have the same number multiple times or even infinitely many times. Here's another one. 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, and so on like that. So this sequence has a special name. This is called an alternating sequence because its sign changes with every single term. And we'll have a lot to say about that type of sequence in particular. All right, here's another one. 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. What was that? Oh, okay. Yeah, be sure you're muted if you're not saying anything here. Anyways, yes, we have this sequence right here. And this is simply just the reciprocal of all of the entries in this sequence right here. Do sequences have to be some kind of function or can it just be an infinite list? I'll show you in a second. There'll be some interesting examples here. But yeah, this sequence goes to show you that we don't just have whole numbers as entries in our sequences. We can have fractions, and we can also have irrational numbers. Like I could put e or pi into my sequence. There's no limits on the numbers that we're going to do put into a sequence. Although we're not going to really deal with complex numbers though, so we're not going to deal with like I or any imaginary number. So we'll forget about that for now. But sequences can have any real number for us. All right. So let's see. Here's another example. 1, 2, 4, 8, 16, 32, 64, 128. So this is the sequences of powers of 2. And this sequence has a special name. This is a geometric sequence. It's where we kind of multiply each entry by the same number every time we go up. And in this case, the number we're multiplying by each time is 2. All right, here's an interesting sequence. 2, 3, 5, 7, 11, 13, 17, 19. Now I'll keep going on. Does anyone know what this sequence is? It's like odd numbers, but you miss a few and they throw 2 in there. Yeah, they're all prime numbers. That's right. So we start with the lowest prime number, which is 2, and the only even prime number. And then all of the rest of these will be prime numbers. So the next number here would say be 23. And that would continue on forever. So someone asked earlier, oh, do you have to have nice formulas for each of your sequences? The answer is no, because there's actually no nice formula for listing the nth prime number. So there's no way to just get instantly what the 168th prime number is, or at least not very easily. So there's not a nice formula for every sequence you can write down. Let's take a look at this sequence. Pi 17 e to the 2021 negative 4.44443 0 6, and then what's the next number? Yeah, there's no like obvious next number here. So sequences can be all it is. It's an infinitely long list of numbers. There doesn't need to be any rhyme or reason to it whatsoever. So this is technically a sequence, though this type of sequence will have limited use for us. We're not really going to look at just a complete list of random numbers here. That's not going to be entirely useful. We're mostly going to focus on the ones that are kind of like this up here, that have some kind of cohesive pattern to them. But this would technically still be a sequence here. Now, as we see, we have a lot of different types of sequences, right? There are a lot of different lists of numbers, a lot of different patterns we can have. And that means that there are going to be a lot of different names and classifications for each of these sequences. Like I mentioned a few of them already, like this one was alternating, this one was geometric, etc. What we're going to do today is we're going to go over a lot of these different classifications. And probably the most important classification that we're going to go over is whether a sequence converges or diverges. Okay, so what does that mean? So converges means the list settles down, and I'm going to put that in quotes, to a specific number. And diverge, all that means is that it does not converge. And we'll see that there are a few different ways that a sequence can diverge here. All right, so let's go back through these sequences that we have up here and see which ones will converge and which ones will diverge here. Okay, so let's take a look at the top one here. 1, 2, 3, 4, 5, 6, 7, 8. It keeps going up through all the counting numbers here. Is that going to settle down to a particular number if we go really far in the list? No, it's not, right? It's just going to keep getting larger and larger and larger and larger. And infinity is not a number per se, so you can't say you're converging to infinity. So that really doesn't count either. So this sequence is going to be divergent. It's not going to settle down to anything in particular. What about the next one? 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. Is that going to settle down to something? Yeah, yeah, it already has settled down to something, and that's 3. So this sequence, said a bad word, converges to 3. So whenever you settle down to something, you say you converge to that number. All right, let's see here. We have 1, -1, 1, -1, 1, -1, 1, -1. Is that going to converge? Yeah, that one's not going to converge because the sequence can't seem to make up its mind whether it wants to be 1 or -1. So it's not really settling down to either one. So this is going to diverge as well. Now notice that this one diverges in a different way than that top one did. This one diverged by getting very large in value. This one diverged by simply not settling down to something. So you can kind of see there are different ways that you can diverge as a sequence. All right, how about this guy? 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. Is that going to converge? Yeah, what is that going to converge to? Right, this is going to converge to 0. So notice these numbers are getting smaller and smaller and smaller as they go along, but they're always going to be positive numbers. So the only possible thing that they could be going towards is 0. All right, how about this next one? 1, 2, 4, 8, 16, 32, 64, 128. Is that one going to converge? Yeah, that one's pretty clearly going to diverge. Even more egregiously than this one is. This one's going to infinity even faster than that. So this one's going to be said to diverge. What about the prime numbers? Is there like an ultimate prime number that they're going to settle down to, or does it just keep going up? Yeah, it just keeps going up, right? There's no biggest prime number, so this is going to diverge. And I think it's pretty clear this one's going to diverge. This one's, we don't even know what this one's doing, so we can't really say it's going to converge to anything. All right, so that's converging and diverging here. And that's probably the most important property of sequences. Now, in general, we're going to like it when a sequence converges, and it's not going to be so great or useful for us when a sequence diverges. So it's important to know how to tell whether or not a sequence converges or diverges. Now, here we can kind of see the pattern here, right? But sometimes sequences, let's see here. Are there infinite? Oh, we have some questions here I want to answer. Are there infinite number of primes? Yes, there are infinite number of prime numbers. You can find prime numbers of any size or greater. When the 1 over x1 never reach 0, that's going to be an important concept in a minute. Even though there's technically no entry where we ever hit 0, it's really about where it's going. And we have a word for that. Does anyone know? Remember the word for that? Yeah, it's going to be a limit. So what we're going to end up doing is we're going to end up looking at a lot of limits to tell us what's going to happen with these sequences in the long run. So it doesn't technically ever reach 0, but we can say it converges to 0 because it's getting closer and closer. Isn't the sum of all positive integers equal to negative 1/12? Oh my God. Okay. This is devolving into memes now. All right, so let's go ahead and get to the next part of this. The next part I want to talk about is it's nice to kind of list things out kind of like this, but eventually this isn't really a great notation because A, it takes up a lot of space to really get the pattern down, and B, it may not be immediately clear what the pattern is going to be. Like, for example, with this sequence, this insane sequence, I could have written it like this, and then maybe the dot, 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 I just start being nice, and I put 0, 0, 0, 0, 0, 0, 0, and it'll converge to 0. So for some cases, we don't really know what the pattern is right away. So we want a more kind of precise way of dealing with sequences. And that's going to come in the form of formulas. So we're going to come up with formulas for sequence. So normally with formulas for functions, we had f of x, right? And this was the input, and then the whole thing was the output. We're going to, or sorry, this is the function name, I should say. Now we're going to use a different notation for sequences, a different notation's customary for these. We're going to use a sub n, where this is how far in the list we are, and then this is the sequence name. So sequences are kind of like functions. In fact, they are functions. They take in a whole number, which tells you what your place in the list is, and then they spit out what number is going to be at that spot. So let's try to see if we can come up with some formulas for these sequences here. So let's start with this one. A sub n equals, well, let's see. When we're in the first spot in the list, we have 1. When we're in the second spot in the list, we have 2. When we're in the third spot in the list, we have 3. Oh, this is name. Sorry about that. My handwriting is really bad today. There we go. Okay. So we have 1 in the first spot, 2 in the second spot, 3 in the third spot, 4 in the fourth spot, etc. What do you think my formula is going to be? When I'm in the nth spot, then what number will I get at? I'm just going to get n. That's right. And while x is the customary variable for functions that we're used to dealing with, n is usually the default variable for sequences. Reason being is that n is usually reserved as a variable when we have whole number inputs. Like it wouldn't make sense to put 1/2 into here because we can't have like the 1/2 spot on the list, for example. So we're going to have a sub n equals n here. All right, what about this a sub n? What's that going to be? I think you'll probably guess what this one's going to be. What's in the 50th spot in the list? 3, right? So what's in the nth spot in the list? 3, right? So this is called a constant sequence, and we have a sub n equals 3 right here. All right, this one's a little bit different here. We have 1, -1, 1, -1, 1, -1, 1, -1. So how do we get it to flip sign? Well, how do we usually flip something's sign? We multiply it by -1, right? So if we keep multiplying this by -1 over and over and over again, it'll just keep flipping signs. So we're going to have a sub n be -1 to the n. Now, if you think carefully about this, you're like, wait a minute. If we have a sub n equaling -1 to the n, then if we go to the first spot, we're going to have -1. If we go to the second spot, we're going to have +1, et cetera, like that. So we can kind of just tweak that, get it to alternate the other way by just putting a +1 there. And by the way, you could have also done -1. That also would have worked well, too. So now if I put in the first spot, I have -1 to the 1 plus 1 would be 2. So we'd have a positive, and then it's going to go thereafter. All right. So let's see here. We have 1, a half, a third, a fourth, a fifth, a sixth, a seventh. I literally said what this one was earlier. It's the reciprocal of what we have up here. So that means that a sub n here will be 1 over n. So a sub n is going to be 1 over n here. And this sequence is something that we're going to be seeing a decent bit. We're going to see this guy a lot, and we're going to see this one a fair bit as well. All right. Now let's see here. A sub n equals what? What's going on here? Multiplied by a bunch of 2's, right? Yeah, so we're going to have some kind of 2 to the n in there, right? But the problem is that if we put in the first spot for 1, then if we put 1 here, it'll be 2 to the 1, which will be 2. And for example, if we put in 2 for the second spot, we'll have 2 squared, which will be 4. So it looks like this is 1 too big. So we can do 2 to the n minus 1. That's an excellent question. So the audience asked, what if we start at n equals 0? Is that a possibility? And the answer is yes. So this is the formula if you start at n equals 1. And a sub n is 2 to the n would be if we start at n equals 0. Yes. So yeah, the issue is like, all right, which one of these do I put? I mean, for example, in Chronos, you need to type in your answer. So which one of these would accept? And in cases like that, we'll let you know. So it'll be like, oh, it starts at n equals 0. It starts at n equals 1. So the answer could change depending on which one of these you start at. And by the way, there's not really a more common one between these two. A lot of times we're going to start at 0, and a lot of times we're going to start at 1. So I can't really recommend one over the other. In fact, we could actually go back here and do the same thing. We could do a sub n is -1 to the n if we start at n equals 0. So as long as you specify which one you start at, you can write it in a number of different ways. Okay, what about this one? All the prime numbers. So I specifically said there's not a formula for that. So we really can't write anything down for that guy. We can't write a sub n equals something with n's and get the prime numbers. That would actually be a massive problem if we could, because a lot of computer encryption algorithms depend on it being hard to compute what large prime numbers are. So if you just had a nice little tidy formula to give you a large prime number, then you could be a dangerous person indeed. Yeah, what's up? So you could do something, you can't write down like a formula, like a mathematical formula for it, but you could write an algorithm to do it. Yeah, so you could write an algorithm to find the nth prime number, and they have various speeds of computing it. But you can't write down a traditional mathematical formula for that. All right. And then there's this is insanity. So we don't have anything for that. All right. So now I want you guys to practice this. I want you guys to practice your pattern recognition skills. And I want you guys to try to come up with a formula for a sequence. All right. Let's see here. So practice 1. Find a formula for the sequence 1, -2 over 2, 3/4, -4 over 8, 5 over 16, and then hopefully that'll be enough for you to decipher the pattern. And we want this formula to start at n equals 1. So why don't you guys take a few minutes here and see if you can come up with a formula for this. What's the fourth term? It's negative 4 over 8. As a hint, I wrote some of these non-simplified for a reason, so you can more easily see the pattern here. You got a lot of right ingredients there, Christopher, but I think you should tweak it a little bit. Yeah, if you see the pattern, but you're struggling to write down the formula, break the pattern into pieces, because there's definitely a few different things going on here. So try to break the pattern up into different pieces and try to come up with a way of expressing each piece. It'd be a fraction? Absolutely. Yeah, we had an example of that as 1 over n on the previous page. And as always, we'll go over in a minute or so. All right, let's take a look at this guy. So I think that there, at least what I can see, I think there are 3 different things happening with this. So what's one pattern that's happening here? Anyone want to volunteer one pattern? Yeah. Yeah, it's flipping signs every other time. That's right. So we have a positive on n equals 1. So this is the place in the list. So we have a positive on n equals 1, a negative on n equals 2, a positive on n equals 3, negative on n equals 4. So if you ever want to have an alternating sign, we need -1 to the n. And then if we just have -1 to the n, the sign will be on exactly the wrong term here. So we can make it n plus 1 to shift it by 1. So we end up having the correct sign here. Although you could also do n minus 1. I think the answer choices probably only say one or the other, though. They say n plus 1 or n minus 1. It should only say one of them. It says plus 1. Okay. All right. So we're going to do this one then. All right. So that's happening. Let's see. What else do we have? Well, we have these powers of 2 in the bottom. 2, 4, 8, 16. So we're going to have 2 to the something down here. Now, if I just have 2 to the n, I'm going to be 2, 4, 8, 16. So that'll be a bit too big. So I'm going to lower that by 1. Then when I plug in n equals 1, I'm going to get 2 to the 0, which is 1. If I plug in n equals 2, I have 2 minus 1 is 1. And then 2 to the first will be 2. Plug in n equals 3. I have 2 squared will be 4. And it seems like it's going to work from there. And then finally, we're not just alternating a sign on top. There's also some kind of thing increasing the value. It looks like we have 1, 2, 3, 4, 5. Well, that's not too hard to put in there. We're just going to put in an n for that. So that's going to give us all the consecutive whole numbers right here. So there we go. Here's the formula for our sequence. And this illustrated a really important point. This is going to be crucial in, well, a good number of lessons, but it's still going to be really important later on. If you ever want to write down a formula for a pattern, break it into pieces rather than trying to write the whole thing at once. Can I go over the last part? Yeah, so in the numerator, I have 1, 2, 3, 4, 5 in the first, second, third, fourth, and fifth spot. So it seems like whatever spot I'm in, I have that number on top right here. All right, so you can't put, no, so if this were non-multiple choice, you could have also done, like this is equal to n, -1 to the n minus 1 over 2 to the n minus 1. It's just it's multiple choice, so there's only going to be one of those. But these guys are interchangeable here. You can use either one of these for any situation. All right, so there's that one. Now let's do our second practice problem right now. Practice 2. Does the sequence from practice 1 converge? If so, what does it converge to? All right, so why don't you take a minute and think about this. Is this going to settle down to a particular number, or is this going to bounce around, or is it going to get really huge or something? That's what we're asking here. All right, looks like some people got some answers already. All right. You guys another few seconds or so. It looks like we got some debate here. So it is alternating and it is getting smaller. So how's that going to pan out? I'm reasonably confident the answer is in 21. Sorry, man. All right. Let's think about this here. So we have our sequence n -1 to the n plus 1 over 2 to the n minus 1. We see that indeed this is going to be alternating. And that kind of seems like a bad omen, right? Because if we remember another alternating sequence that we had before, that one diverged because it wouldn't settle down. But the thing is that this right here, we could rewrite this as n over 2 to the n minus 1. And then we have -1 to the n plus 1. So this part right here, if we just only look at this, what is this doing as a sequence? Well, let's see here. So we have just the consecutive counting numbers on top, but then we have powers of 2 on the bottom. And we actually encountered both of those already today. We look at how big the counting numbers are getting versus how big the powers of 2 will be getting. Which one's going to be bigger in the long run by far? The powers of 2, right? So we have a smaller number up here that's getting divided by a bigger number down there. So what's going to happen as n gets larger, this difference only gets more extreme. This is going to go to 0. So we end up having something heading to 0. So then 0 times -1 to the n, or any negative or positive just 1, will end up being still 0. So it turns out that that alternating isn't that bad as long as what you're alternating is heading to 0 here. Yeah, so we have a comment here. Yeah, both the negative and positive versions. So we have -1, negative a half here, and then 1, 3/4, 5/16. Both of those, what are called subsequences, are getting closer to 0. So that's further evidence that this is going to go to 0. This converges to 0. Okay, now how would we do this? So if you're a math major, you may be a little bit concerned. Okay, well, you're kind of just saying loose words like small and big and evidence of, but that's not good enough for me. How can we show definitively that this is going to go to 0? And the answer is that to show convergence, we take a limit. So to really see what's going on here, we would look at the limit as n goes to infinity, a base of n, which is the limit as n goes to infinity of n -1 to the n plus 1 over to the n minus 1. So what we would do is we would do this limit right here, and then we would see as a limit, this is going to go to 0. So if you ever want to be absolutely sure if something is going to converge or diverge as a sequence, all you need to do is look at the limit. That's really what's going on here. All righty. So let's take a look at an example and see if we have some other, or let's practice seeing if functions or sequences converge or diverge. Okay, so let's take a look at a few of these. So, and this will give us a chance to review limits if we're a little bit rusty. We have 4n cubed plus n squared plus 1. All right. And then that's going to be divided by 3n to the 5th plus 16n plus 2. All right, so we want to know if this converges or diverges. Which one is this going to be? Well, like I just said, the definitive way to know is to look at the limit as n goes to infinity. As we get super far along in the list, what's going to happen? Well, let's see here. So what we're doing is we're going to take a limit of a rational function, right? A polynomial over a polynomial. So let's review how to do that. So this limit right here depends entirely on the degree of the polynomial on the top and the bottom right here. So for example, we have 4n cubed plus n squared plus 1. This is a degree 3 polynomial. And then down here, we have 3n to the 5th plus 16n plus 2. This is degree 5. Now, if the denominator has a larger degree than the numerator, what's going to happen? It's going to go to 0. That's right. So the degree of the denominator is bigger than the degree of the numerator. Let's say I flip this upside down. Let's say the 3n to the 5th part was on the top and the 4n cubed part was on the bottom. What would happen then? What would that limit be? It would go off to infinity. That's right, because this is a stronger function. It goes to infinity more quickly than this. So if it's on the numerator, then your numerator is getting really big compared to the bottom. That's going to go off to infinity. What if they're the same degree? So what if this was like, say, 4n cubed over 3n cubed right here? What would happen in that case? Does anyone know? Yeah, we read off the leading coefficients. That's right. So it's going to be 4/3 in that case, if they were the same degree. So we're going to be seeing a lot of things like this. We're going to see a lot of limits of a lot of rational functions. So make sure you're comfortable with the 3 facts that we just went over here. All right, let's see here. I don't think we have time to do all of these and still get to the last part of the material here. Let's see here. I'm going to do B and then I'm going to do D. All right, so here we have 2 to the n over n to the 100. So we need to see if this is going to converge or diverge. What was the third case? The third case was when the degree of the top and bottom were the same. Then we look at the leading coefficients for the limit. All right. So Bn is 2 to the n over n to the 100. So let's see what happens if we do the limit as n goes to infinity to see if this converges or diverges. All right, so what do you guys think? We have 2 to the n divided by n raised to the 100. What do you think about that? Think diverges? But we're raising something to the 100th power. Like, that's pretty big. Yeah, so even though we're raising something to the 100th power, we're multiplying it by itself 100 times. What we're doing on top is we're multiplying 2 by itself effectively an unlimited number of times. So remember, exponents mean we're multiplying this many times. So even if the number we're raising to the 100 is pretty big, we're still only multiplying it by itself 100 times, whereas 2, we're going to eventually multiply it by itself billions, trillions, infinitely many times. So it turns out that exponential functions go to infinity faster than even the highest powered polynomials. So this is going to go to positive infinity. And this brings me to something that's going to be incredibly useful, which is called the hierarchy of functions. So there are a lot of different functions. So this diverges. I guess we should say that. So there are a lot of different functions that go to infinity. So if we take the limit as x goes to infinity of ln of x, that goes to infinity. We take the limit as x goes to infinity of x squared, that goes to infinity, of x cubed, x to the fourth. If we look at 2 to the x, that goes to infinity, and so on. But they don't all go to infinity at the same speed. So which ones go to infinity faster? Lowest on the totem pole are natural logs. While these technically do go to infinity, they go so extremely slowly. So slow, in fact, that their graph almost looks like it's leveling off, but it's really not. It just very slowly goes up. So that's lower on the totem pole than n to a fixed power, where a is greater than 0. And by the way, this double inequality means goes to infinity faster than. All right, so n to a power goes to infinity faster than natural log. But if we have a to the n, where a is bigger than 1, meaning we have an exponential function, that's going to go to infinity even faster here. Now, are exponentials top dog here? They're going to be the king? Not quite. So there's something that you guys may have seen before, but maybe not, called n factorial. So does anyone happen to know what n factorial is? What's a factorial? Yeah. Right. Yeah. So what we do is we start at this number right here, and then we multiply down by each consecutive number. So n factorial is n times n minus 1 times n minus 2. And we keep descending through all of the whole numbers, and then we get to 3 times 2 times 1. So that's going to be what a factorial is. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Let's see, 5 times 4 is 20, times 3 is 60, times 2 is 120, and then times 1 is 120. So you see, all we had to do was input a 5 into this and outspat 120 right here. So factorials grow even faster than this because just like exponentials, they're multiplying by more and more numbers. But the thing with factorials is the numbers are getting bigger that you're multiplying by. So that's why factorials end up being bigger. All right, is this the fastest growing function? No, it's not. We can even grow faster than that by doing something like n to the n, for example. Now we're not even burdened by all of these lower numbers. All of the numbers we're multiplying by are continuously getting bigger. So this one's getting even bigger. And of course, you can kind of mix and match these and combine them to get even larger functions as well. So there's really no end to this list right here. We can combine, we could always combine 2 of the smaller ones and possibly get larger ones here. But the ones listed here, these guys, these are the ones we're actually going to be seeing here. But in theory, they go on forever. Yeah, you'll see in a few assignments, we're going to have something interesting with that. Yeah, so we could have like a factorial of a factorial. But yeah, but what does all of this mean It means that if something lower on the list is above something higher on the list in a fraction, that's going to go to 0. So, and in the other way around, if we have something higher on the list divided by something lower on the list, that's going to go to infinity. Oh, the mic's buzzing? Yeah, we had this problem last period. Is that better? Is that okay? It's good? All right, wonderful. All right, I'll explain what I was just doing again. So functions that are higher on this list divided by ones that are lower will go off to infinity. So we just saw an example of that. So we have 2 to the n, which is in this category, divided by n to the 100, which is in this category. So since the bigger one's on top, we have something big over something small, that's going to go to infinity. And then if you flip it around, if we have something lower on the list divided by something higher on the list, that's going to end up going to 0 because we're going to be dividing by a larger and larger quantity as we go along. So this is an important thing for evaluating limits. This is extremely useful for doing that. So I would definitely recommend learning this list right here. Okay, let's see here. Oop. I'm going to have to skip C and D as examples. I'll post those either today or tomorrow. I want to get into some other ways that we can classify sequences. So we have the distinction between converging and diverging. And I think I, in passing, mentioned a few other distinctions earlier. So what are all of these? So I'm going to quickly kind of go through this laundry list of things, of different ways we can label sequences. So an increasing sequence. Intuitively, that means the numbers are getting bigger as we go along through the list. So that means that an plus 1 is greater than or equal to an. And so something that would satisfy that would be 1, 2, 3, 4, 5, 6, 7, etc. So you see all of the consecutive numbers are getting larger and larger and larger, or at the very least, staying the same size. Notice we have an equal to there. And then I could bet you can guess what decreasing is. An plus 1 is less than or equal to an. So for example, we could have 0, -1, -2, -3, -4, and that would be a decreasing sequence right there. All right. Let's see here. Here's an interesting word you may not have seen before. I can write it. Monotonic. So what is a monotonic sequence? Well, let's think about what monotone is. It's kind of boring. It's doing the same thing over and over and over again. So a monotonic sequence is either always increasing or always decreasing. So if you're one of these two, then you're going to be monotonic here. So monotonic is kind of just a general term that encapsulates both of these, because sometimes we're going to encounter something that works for increasing and then it also works for if you're decreasing as well. So rather than just saying increasing and decreasing, we're just going to combine those and say monotonic. So if you're one of these, then you're going to be this one here. Okay. That's another term we need to know. Bounded means the sequence doesn't go above a certain point or below another point. It means the values are sort of fenced in, like it can't go below a certain value and it can't go above a certain value. So an example of a bounded sequence would not be one of these because these decrease, for example, without end and increase without end. So why are both less than or equal to? What happens in a constant sequence? Yeah, so according to these definitions, a constant sequence where all of them are equal would be both increasing and decreasing, as ridiculous as that sounds. But that's the only example of that. That's kind of a degeneracy in our terminology. Mathematically, it's going to be more convenient to do this in the future, use the equal to signs. But yeah, there is that little technicality there where a constant sequence is both of those. So you're right about that. But Trust us, it's going to be more convenient in the future to do it this way. So would 1 over n be bounded to 1 and 0? That's an absolutely great example. So if we have 1, 1/2, 1/3, 1/4, 1/5, and so on, this sequence is bounded above by 1. 1 is greater than or equal to everything we have in here. And we could say it's bounded below by 0. All of these are going to be positive numbers. So since it's bounded above and below, we can say that this is a bounded sequence. It kind of has a limit to how big and how small it can be. Would 1, -1, 1, -1, 1, -1 be bounded? Absolutely. It'd be bounded above by 1 and then bounded below by -1. So that would also count as bounded. Yeah. That's right. Yeah. So if we have a sub n, so someone asked, would sine be bounded? And yeah, if we have a sequence where a sub n is sine of n, then this would be a bounded sequence as well. It'd be bounded by 1 and -1. Absolutely right. Okay, now one interesting fact here is that monotonic plus bounded equals convergent. So if you are both monotonic and bounded, then you are automatically going to converge as a sequence. And why is that? Well, remember, if you're bounded, you effectively kind of have like a wall up here and a wall down here, right? And then if you're monotonic, you need to be going in one direction. So if you're going in one direction, you're eventually going to run into one of these walls and you're going to be forced to settle down right here. For a sequence to be bounded, it has to have an upper and lower bound. That's right. So if you say unqualified bounded without one of these adjectives here, then yes, yeah, you need both above and below for that. All right, just a few more of these, and then we'll be good to go. Alternating. I think I defined this earlier. Flip sign on every, and I mean every, term. So a sub n is -1 to the n. That one works out. A sub n is cosine of pi times n. That one works out because no matter if we have cosine of a multiple of pi, that's always going to be 1 or -1. So it's going to split between positive or negative. One thing that's not alternating, even though it seems like it might be, is sine of n. So while it does frequently flip between positive and negative, it doesn't do so regularly enough in order to be truly alternating. So occasionally we'll have like 2 in a row that will be positive. So it's very strict about that. We need to have everything alternating for every single term. So that's not going to count as alternating. All right, we have 2 more terms here. Geometric means that you multiply by a number to get the next term. And a simpler way of saying this, you could think of it as exponential. So for example, an is 2 to the n would be a geometric sequence because every time we go forward, we multiply by 2 to get there. Another example might be 4 times maybe 3 to the n, like that. So we would have 4, 12, 36, 108, etc. We're just multiplying by the same number every single time to get to the next level. And then finally, this one's not going to really play a huge role in this class, but I want you to be exposed to this for when it does play a large role in differential equations. A recursive sequence is where the next terms are defined by the previous terms. So for example, let's say we have a sequence where a sub n is a sub n minus 1 plus a sub n minus 2. So if we say maybe a1 is 1, a2 is 1, then a3 will be the sum of the previous 2, which will give me 2. A4 will be the sum of its previous two, which will give me 3. A5 will be the sum of its previous two, which will give 5. And by now, I think the chat's got it. That's right. So this is called the Fibonacci sequence, where we add two of the previous numbers together to get the next one in the list. And this is an example of a recursive sequence, where the next number is defined in some way based on the previous ones. Now, we're not really going to be seeing this one too much in here, but I at least want you to like have heard of it when you get to the future class here, so they don't yell at me. All right, and I think we're over time now. Oh, definitely. Sorry about that. Anyways, I'll post the solutions to the stuff that we didn't get to today. And tomorrow, or not tomorrow, on Wednesday, we'll generalize this notion of sequence to something called a series. So I'll see you guys next time.